Okay, hi Year 12. Another video here talking about shapes of molecules and how to work out what shape they'll have. But starting really from the basics, because I realised that between the videos that I asked you to watch and the work that I sent out yesterday, there seems to be a bit of confusion creeping in. So I'm going to take it back to basics. I'll keep it fairly simple for these first few examples, and then we'll build up over this and some subsequent videos. The overall aim here is both to understand how to work out what shape a molecule has, but also how to answer an exam question where you're asked what shape something has. So I'm going to be setting you some exam questions that rely on the sort of thought process that we're going through here, and I'll be getting you to submit those exam questions so that we can have a look at what we should be putting for those. So the first example that we've got is aluminium trichloride, and this is quite a, when the camera comes back into focus again, this is a bit of a sort of classic example. There we go. And the first thing that we want to do when looking at the formula aluminium trichloride is trying to decide what our central atom will be. And in most cases, this will be the atom that's unique in the formula. So in aluminium trichloride, there's only one aluminium and there's three chlorines. So our central atom is going to be aluminium. Next, we go to our periodic tables and we look what group our central atom is in, and that will tell us how many valence or outer shell electrons that atom has. So for aluminium, I look up on the periodic table and we know that it's group 3, so we put 3 electrons around our central atom. I know that my aluminium here is bonding to chlorine, that chlorine is in group 7, and that because it's in group 7, each chlorine atom needs a share of 1 extra electron and needs to form 1 covalent bond. So I know that if I put a chlorine here with its 7 electrons from its outer shell, that will give me a closed shell configuration for chlorine. And if I do that with all 3 chlorines from the formula AlCl3, I end up with this. And there are a couple of checks and balances that I mentioned that you need to make sure that you're doing when drawing a dot and cross diagram like this. And that is to make sure that not only does the central atom have as many electrons shown from its outer shell as it should, in this case aluminium should have 3 because it's in group 3, but also that any other atoms that it's bonded to have the correct number of outer shell electrons as well. And in this case, each of my chlorines has 7 electrons because chlorine's in group 7, so 7 electrons in the outer shell. And this is it. That's the dot and cross diagram successfully drawn for aluminium chloride. The next thing we need to do is look at the number of bonding and non-bonding pairs surrounding our central metal atom. Our central atom, in this case aluminium. Now, we can think of each of these bonding pairs, and we'll see some non-bonding pairs or lone pairs later as well. We can think of these as areas of electron density, places where we find electrons, and there are 3 around our aluminium trichloride. Now, in the textbook, you have a list spread out across 3 or 4 pages of all of the different shapes that you have depending on the number of areas of electron density. And I'm going to give you a summary table as well to remind you of what shapes things form depending on how many areas of electron density we have around our central atom. In this case it's 3, and there's nothing else surrounding that aluminium, so the shape is going to be triangular planar. And at this stage, that is something that you need to know. That is a factual piece of information. If there are 3 areas of electron density around the central metal atom, the shape is going to be triangular planar. So there is some memory required here as well as some understanding of how to draw the dot and cross diagrams. Just building up from that, if it is triangular planar, then the diagram I'm drawing here actually counts as a, if I do it properly, the diagram that I'm drawing here would count as a 3D representation because the word planar means flat, and aluminium trichloride is a flat molecule. The bond angle between each of these chlorines, and I could pick any chlorine-aluminium chlorine bond to describe the angle here, the bond angle is 120 degrees. And that's because these areas of electron density these negatively charged electrons have repelled to get as far apart from each other as possible and to minimise the repulsion, maximise the separation. So in that language there, we're beginning to lay the foundations of how we're going to answer an exam question on this. But for now, I just want to keep going through, looking at some examples and working out how we'd both draw their dot and cross diagrams, figure out their shape and bond angle. So the next example that I have, handily prepared and ready to go, is our ammonia molecule, NH3, when it comes into focus. We've got our ammonia molecule here. Okay. And when I look on the at the formula NH3, let's have some focus. Yep. When I look at the formula NH3, my unique atom is nitrogen, so that's the one that's going to go in the centre of my dot and cross diagram. Okay, nitrogen, look it up on the periodic table, is in group 5, so I put in my 5 outer shell electrons around the outside of my nitrogen. And I can see that, or hopefully I can see that there are 3 sort of obvious places where we might form covalent bonds here. 3 opportunities around my central metal atom, around my central atom to form bonds. And in fact, bonding to 3 hydrogens, that's exactly what we're going to have. Hydrogen has 1 electron in its outer shell. It needs a share of a second electron in order to form this stable configuration. And so we end up with NH3 looking like this. Not sure why the focus is struggling so much here, but there we go. So there's our ammonia molecule. And I double check that I've drawn the correct number of electrons for each atom. For my central nitrogen atom, I've drawn 1, 2, 3, 4, 5, which is correct because it's in group 5. And for each of my hydrogens, I've drawn 1 electron, which is correct because they only have 1 electron. Now, the shape of this is no longer a trigonal planar shape that we had on the one before, because now, as well as our 3 bonding pairs of electrons, we also have this non-bonding pair of electrons. Okay? Now, all areas of electron density repel one another. And so instead of having 3 areas of electron density, we now have 4 areas of electron density repelling one another. And the 3-dimensional shape that they form, if there are 4 areas of electron density, is going to be based on a tetrahedral shape. It's going to be based on tetrahedral. Tetrahedral would see 1 atom in the centre with areas of electron density above, out to the side, pointing down and coming towards us, pointing down and going away from us. So this is our tetrahedral shape here, and this is the basis of the shape that we find for ammonia. However, one of the areas of electron density here is a lone pair. It doesn't lead to a bond. So the shape that we actually see for ammonia, very, very similar, but the lone pair at the top here, which I've drawn as 2 crosses in my dot and cross diagram, that lone pair there, we don't, there's no atom on the end of that, so it doesn't form part of our overall shape. So we still have the bond coming down here to this hydrogen, we still have this one here, and we still have this one here. So when we're drawing this as a 3-dimensional structure, we have our N there, one of our H's here, one of our H's here, and one of our H's here. So this one's coming in front of the plane of the paper towards us. This one's going away behind the plane of the paper, away from us. This one's flat in the plane of the paper, level with the paper. Now this shape here, if you imagine the nitrogen at the apex at the top of a pyramid coming down on 3 edges to the bottom of a triangular shaped pyramid. So this is trigonal pyramid, is the name of that shape. So it's based on tetrahedral, it's based on a shape with 4 areas of electron density, but because one of those isn't a bond, because one of them is a lone pair, the shape we end up with is a trigonal pyramid. Okay. The bond angle, if this was tetrahedral, if it was a perfect tetrahedron, the bond angle between these would be 109.5 degrees. As it is, the lone pair of electrons at the top of our molecule here, they're not being shared between 2 atoms. So all of that electron density, all of those electrons are spending time down here on the nitrogen. And because of that, it has an extra repelling effect compared to a bonding pair of electrons. And that squeezes these and forces them closer together, because this is more repelling of these bonding electrons than they are of one another. And that means the bond angle goes from 109.5 in a perfect tetrahedral arrangement to 107 degrees where we have a lone pair. So in our trigonal pyramid, the bond angle is 107. Our next example is phosphorus pentafluoride, PF5 here. Okay, and again, we get the old faffing around trying to make it focus and the slightly wobbly, seasickness inducing wobble there. Right, okay, so phosphorus is in group 5 of the periodic table, and that means it's got 5 electrons in its outer shell. And if I went round and did what I did with nitrogen and paired them up at the top, that would give me only 3 places available to form bonds with fluorine. However, because we're forming 5 covalent bonds between phosphorus and 5 fluorine atoms, all 5 of phosphorus's outer shell electrons are going to be involved in bonding pairs. So we end up with 5 bonding pairs of electrons around the central phosphorus. How do I know that? Well, because phosphorus is bonded to 5 things, and in order to be bonded to 5 things, it must share all 5 of its outer shell electrons. That might look odd to you, because we now have 8 electrons around our central, we have 10 electrons rather than the usual 8 around our central phosphorus atom there. But this is possible, this does happen, and we see this in naturally occurring compounds. I haven't finished yet. I may have drawn the 5 crosses to show the 5 outer shell electrons of phosphorus, but I haven't drawn all of the electrons of our group 7 fluorine atoms. So this will take a little time, but we go through and we put in all 7, so an extra 6 on each one, all 7 of the outer shell electrons of each fluorine, and we end up with this. So yeah, not a quick one to draw, this one, but now we have our phosphorus bonded to 5 fluorines. Now, if you look on your table of shapes, on your summary table of shapes that we're going to have, we'll see that when we have 5 areas of electron density, 1, 2, 3, 4, 5, and they're all bonds to atoms, they're all bonding pairs to atoms, the shape that we get is trigonal bipyramid. Now, a trigonal pyramid would be a triangle base coming up to a point, 3 edges going up to that point. A bipyramid looks exactly the same, but almost reflected in a mirror downwards as well. So 2 pyramids, if you like. So our phosphorus goes in the centre here, and one of our fluorines we can draw flat with it in the plane of the paper. We can have one going up above the phosphorus, one coming down, and these are going to form the top and bottom points of our pyramids. And then we have a fluorine going away from us, and a fluorine coming towards us, or a phosphorus to fluorine bond coming towards us. And these 3 form the flat triangular base of the upward pyramid going up to this fluorine, and also the flat triangular top of the downward pointing pyramid coming down to these. So it's 2 pyramids, bipyramidal, trigonal bipyramid. Okay. Now, the bond angle here, if you were to build a model of this, the bond angle here is a little bit different because we've got 2. The bond angle between the ones pointing straight up and the one pointing straight out to the side, and the same here, these are both right angles. They're both 90 degrees. But the bond angle between our fluorines around the centre here, well, it's a complete circle around the phosphorus divided into 3, so that's 120 degrees. So we've got 2 different bond angles going on in our phosphorus pentafluoride there. It's a trigonal bipyramid, and we have 5 areas of electron density spread out with 90 and 120 degree bond angles. The penultimate one that we're going to look at is actually one of the simpler ones. Beryllium is in group 2 of the periodic table, so it has 2 electrons in its outer shell, and it's bonding to 2 chlorines, so it's going to form a simple covalent bond, a nice straightforward single covalent bond to each of those. Again, this might look a little bit unusual as I fill in the outer shell electrons of both of the chlorine atoms to ensure that I haven't missed any outer shell electrons off any of my atoms. This is going to look a little bit unusual because, again, instead of 8 electrons around the central atom there, beryllium has only got a share of 4, but this is a stable occurring compound. You can probably already see the shape that this is going to form. We've got 2 areas of electron density this time, and when we have 2 areas of electron density, the shape is called linear. And again, learning what shape you get when you have different numbers of bond or non-bonding pairs, learning what shape you're going to have is just some factual information you're going to need to recall. They are able to get nice and far away from each other. In fact, they can sit on complete opposite sides of the beryllium atom in the centre here, and so we have a bond angle within a linear molecule of 180 degrees. The last one I was going to look at was chlorine trifluoride, and again this might seem a little bit odd as we come to draw this. You will probably think of chlorine being in group 7 as needing to form one bond in order to have a share of a full outer shell of electrons. However, here it's obvious that chlorine's our central atom, because there's only one of them, but that it's bonding to 3 fluorine atoms. So what I'm actually going to do first is draw out my chlorine and then form those covalent bonds to the 3 fluorine atoms that it's going to form covalent bonds to. So there we've got a bond to a fluorine, and a fluorine. Fluorine being in group 7, 7 electrons in the outer shell, I need to make sure once again that I've drawn the outer shell electrons of all of the atoms. But I haven't actually finished drawing them for chlorine here, because I've got 3 outer shell electrons involved in this bonding, but chlorine's in group 7 as well. It's also got 7 electrons in its outer shell, of which I've only drawn 3 so far. So the remaining 4 sit over to the side, and as we've met so far, when we're talking about electrons, we're talking about them being paired up. So this time we have 3 bonding pairs of electrons and 2 non-bonding pairs of electrons. So we have 5 areas of electron density in total, but only 3 of those are in bonding pairs of electrons between the chlorine and the fluorine. So 5 areas of electron density, it's going to be based on the shape that we've just seen, on trigonal bipyramids. But just as when we saw ammonia was like a trigonal shape, but was missing, it was like a tetrahedral shape, but was missing one of the atoms that was necessary to make the full tetrahedron. This is based on a trigonal bipyramid, but is in fact missing 2 atoms that it could be bonded to, so we've got 2 non-bonding pairs. And that affects the shape. So if I do a very quick reminder, if we were looking at a trigonal bipyramid, we'd have one going up, one going down, one going away from us here, towards us here, and one out to the side here. Now in this case, these non-bonding pairs want as much space as possible. They're more repelling than the bonding pairs. And the place where they can get more space than they would have elsewhere is in these 2 positions here. If we put one of our non-bonding pairs here and one of our non-bonding pairs here, they are as far apart from each other at 120-ish degrees as they can get. So they pick these positions here. There are examples, and you will see examples, where the non-bonding pairs will be above and below, leaving you with a trigonal planar shape of 3 bonds in a flat triangle shape. But here, our non-bonding pairs are out to the side. If you've got a question on this, you wouldn't necessarily know whether it was going to form the shape I'm about to mention, or those 3 atoms, those 3 bonds forming around the centre on the flat. So either answer would be acceptable. Okay. What we actually get this time is called a T-shaped molecule, not like the drink, sadly. A T-shaped molecule, okay, where we have our central chlorine here. We have a fluorine pointing up, a fluorine pointing down, and a fluorine pointing over to this side. We do have our 2 non-bonding lone pairs sticking here and here in these positions. And because they have a slightly extra repelling effect, instead of being 180 degrees from each other here or 90 degrees from each other here, these actually end up as about 89 degrees, so they are squashed or compressed slightly by the presence of these non-bonding pairs of electrons. But this is our T shape, and we can effectively get away with drawing it in 2 dimensions because the bits that would be 3D, that would be going away from us and coming towards us, are lone pairs in this case, so they haven't got bonds with atoms on the end of them. So, hopefully what we've picked up from this is that we need to be able to look at the formula for a molecule. We need to be able to use that, having worked out what the central atom is, we need to use the periodic table and the number of electrons in the outer shell to draw a dot and cross diagram, not forgetting any electrons on those atoms that aren't at the centre. And once we've drawn our dot and cross diagram showing the bonding and non-bonding pairs, we need to count them up, see how many areas of electron density or how many bonding and non-bonding pairs there are, and then use that to work out the shape. The step between counting the areas of electron density and working out the shape, that is based on learning the different shapes. So learning what shape we have when we have 2, 3, 4, 5 or 6 areas of electron density, from linear at the most simple with 2 all the way through to octahedral where we have 6. Once we've done that, once we know the name of the shape, we can work out what the shape will be specifically, particularly where we have non-bonding pairs of electrons that take us from an original shape on which something is based through to a modified shape that takes into account those non-bonding pairs of electrons. Okay, so I'm going to give you some examples to have a go at drawing dot and cross diagrams for and working out the shapes. I'm going to give you that summary table of shapes based on the number of areas of electron density, and I'm also going to give you a couple of exam questions to have a look over, and then I'm going to give you a couple of model answers, just basically pointing out what you need to say, which bits you need to include when answering a question about shape. Okay, thanks for your time.